Hello, good morning. My name is Guillaume Tarel. I work for Hydro-Quebec, which is a power generation company in the Quebec province of Canada. Before I start, I would like to say I'm happy and grateful to have the opportunity to present today, even in those special circumstances. And well, I really wish we will have the opportunity to meet again and have live discussions as soon as possible. Um, the work I'm presenting today is mainly based on work done by my two coworkers, Odun Botterud and Magnus Korpas. Odun is a principal research scientist in the MIT Laboratory for Decision and Information Systems. And Magnus is heading the research group Electricity Markets and Energy Systems Planning at the Department of Electric Power Systems at NTNU in Norway. And it's actually their work, the work that they did, which we have extended recently and that I'm presenting today. And the topic is the profitability of market participants in decarbonized power systems. Um, so this is the outline of my presentation. I will start with something that we actually all know, and which is the topic of this conference. It's pretty likely we're going and moving towards a future with more variable renewable energy, and mostly solar and wind. And so I will shortly discuss that point, and then move on to discuss how markets were in the beginning, power markets were in the beginning designed to be efficient and fair. We discuss what efficient and fair means, but that they were designed initially for thermal generation mostly. And so we will address the efficiency of such markets to work with variable renewable energy, mostly energy-only markets and markets with capacity. Before I start, there is a caveat, of course. What I will show you is based on a theoretical model. So I will show you equations and models and everything. But we should not forget that, of course, those models simplify the reality. So models such as the one I'm going to show you, they give very good insights, but they cannot be used to make like direct market design conclusions with only those models in hand. In this slide, I show you a graph from the Net Zero World Roadmap from International Energy Agency, which was released earlier this year. And it shows that at the world level, between 2010 and 2050, PV, so photovoltaic and wind, are going to increase to eventually become the largest generation sources in the world if we look at the announced pledges case from the IEA. So, and this is just an example, since you know there are many studies that have similar conclusions with lots of solar and wind coming online. There is the NARI study by Enrel from this year, for example. So, of course, there is an interesting technical aspects in such studies. So, what's the feasibility of such a power generation mix? Is it possible to have lots of wind and solar PV? How is it going to work? Should we have storage and everything? And technical studies are mostly not based on cost. And on top of that, there are also various economic aspects which are interesting as well. So first, how much is such a power generation mix going to cost overall? That's the first interesting question to ask. And then whether there's the question of whether every participant or every generator gets a fair revenue from the power market. And those two questions, so the overall cost of such a system and the fair revenue are the topic of our research and of this presentation. So I'll start. Remember, I just said one of the interesting questions is the fair revenue question. So of course, one wants every competitive power generator to be able to recover its cost. Otherwise, such a generator is not going to stay online. And this question of the fairness of the revenue was addressed and indeed solved quite a while ago during the foundation of power markets. And there is lots of very interesting and fundamental papers that can be found actually in the literature section of this paper here. But the basic idea behind that is to minimize fixed and variable costs for a power generation system. So this is what is described as this equation. We want to minimize the fixed cost. So this here is the fixed cost per megawatt of a generator. This is the installed capacity of a generator. And this is here the variable cost of a generator and the total energy generated by this generator. And what we want is to minimize that function. And so in this example, it's pretty simple. I only have two generators which have to meet the sorted load duration curve. So this here is the time from, let's say, 0 to 8760 hours, which is the number of hours in a year. We sort the load from in a decreasing fashion, and then we have, in this example, only two generators which are able to meet the load, which are the base generator and the peak generator. And the cost minimization, so there is lots of mathematics behind it, but the cost minimization, it leads to an optimal size and therefore an optimal duration for each generator. So for example, the base generator has this optimal size, and it's going to run throughout all the hours of the year, while the peak generator here has this optimal size and is going to run during only those hours. The beauty of the analytical solution for this, which is described in this paper, is that it solved the two issues that I described previously. So the optimal solutions for this problem leads in the same time to the least expensive solution for the system as a whole, and to a fair profit for each generator. And note that the extension to the case with many generators is straightforward. And one can show that at optimality, the energy must be priced at either the value of lost load during scarcity events, so during those hours that have a very big demand here. And for all other hours, the energy should be priced at the marginal cost, so during the rest of the time. So for example, here, during this period of time, the peaker is the marginal generator, so the energy should be priced at the variable price of the peaker. And by doing this, so using a marginal cost, all individual generators, they are able to recover their costs. So let's say, to make it simple, they get a zero profit. And what's interesting is that those basic principles which I described in the slide before is what's implemented in practice. So this figure here on the right illustrates the equilibrium between the supply. So each bar here is the supply offered by the generators with their proposed price, and here are the megawatts. So this figure here illustrates the supply between the equilibrium between supply and the demand at one given hour of the day. So this graph here is from ISO New England. So the available supply for each generator is sorted according to the marginal cost. And once we reach the level of demand for that specific hours, the price that clears the market for this specific hour is given by the marginal generator here. So we have the low cost big generators here on the left, such as nuclear generators, the higher cost generators as a diesel generators there on the right, and the price is given by the intersection between the marginal generator and the demand level. And of course, then this is for one specific hours, but then the prices can vary by hour of the day, by season of the year, by prices of the fuels, location, etc. And the question we asked ourselves is, with lots of variable renewable energy, is it still going to work? Because of course, variable renewable energy has no such thing as a variable price. So in the case of VRE, the price, the variable price is actually zero or very small. And the nice thing is that if we go back to the graph we had before with the load duration curve here, and we add variable renewable energy. So we are left with the new net load duration curve here, which is the load duration curve as previously minus the variable renewable energy generated for each hour. And we use the same mathematical formalism as before. And the good news is that using the same type of model as before, one can find a new optimum. So a new optimal size for each generator. If and for each generator, we are left with a fair revenue and everything. So the thing is, the formalism and the fact of using prices described as the marginal as the price of the marginal generator are still working to find an equilibrium. So as long as certain conditions apply, which are mainly that viable renewable energy can be curtailed, which is absolutely necessary in those calculations, and that of course variable renewable energy has to recover some of its costs through the market. So either we assume no subsidies, or the subsidies are not large enough to cover all the costs of variable renewable energy. So the model would also work with subsidies, but the main point I would like to say here is that we can include variable renewable energy in the competitive equilibrium. So we can find an optimal sizing for the base generators, the peak generator, and for the renewable generator as well. Now, so I've shown you previously how it works with Energyonly, that we can find optimum capacities that meet the load duration curve. So we have the load duration curve here, and there are mathematical equations which will give us the optimal sizing of the base generator and of the peak generator. But now the question is, and the question was when during the foundation of power markets, if this is not enough, if for any technical reason we would like to have a total generation capacity which would be this red line here, so somewhere higher than the Energyonly optimum. What a typical solution to that issue is to add a capacity requirement. So it's a solution with two main parameters. So a total capacity requirement, which is this red line here, which would be computed by engineers in a way. So for example, there is the 1 in 10 years rule for disconnecting non-interruptible customers. But let's say that outside of the Energyonly, we would have a capacity requirement, and then we would have a capacity contribution for each generator. So each generator would be given a capacity contribution depending on its ability to be able to generate during peak hours. Okay, and the result of having a capacity requirement and a capacity contribution is eventually a capacity price, which is settled in an auction process. So this is the way modern capacity markets are designed in a way. And what we did is that we started with the Energyonly model, which we described in the previous slide, and we extended it by adding a capacity constraint. First, we did that using no variable renewable energy. So using the analytical modeling, we could show that, of course, the capacity constraint, they would distort the Energyonly fair revenue. The thing is, if 100% here is the case with no capacity requirements. So let's say we leave the model work with Energyonly. In that case, we know that the profit loss, or that the profit for each generator is zero. So each generator gets a fair revenue from the market. If we increase the capacity requirement, so we increase the total generation that's needed, then there will be a profit loss for each generator. So in this case, it's with only 2 generators to make it simple. So the base generator will suffer a profit loss, which in percentage is pretty small, and the peaker will experience a profit loss, which is larger. So because of this profit loss, if we want to restore fair revenues for generators, we have to pay them capacity payment. And one thing we can show from our analytical model is that the same dollar per available megawatt payment must be paid to each generator to restore fair revenues. And another thing which we can see from that graph is that the peaker capacities and revenue are extremely sensitive to the capacity requirement and capacity contribution of the peaker. Now moving on, what we did afterwards is to add a variable renewable generation. So remember that in this case, we've shown that there is a load duration curve here, that we get a net load duration curve here in solid black once we remove variable renewable generation from the load duration curve. And we've seen that in the energy-only fashion, we can derive optimal capacities for the base generator, the peak generator, and the variable renewable generator. What we did again is to extend our model and to add capacity constraint. What we show is that a capacity payment must be made to each generator in proportion of its on-peak contribution to restore fair revenue. There is an analytical solution for the optimal sizing of each generator, and I won't go into the details of this formula, but let's say we can derive an optimal capacity for each generator. And so a capacity payment should be made to each generator, and the capacity payment to variable renewable energy generator should be in proportion to their contribution at the time of peak, and which usually is pretty small unless, of course, the variable renewable generator is accompanied by a dedicated storage. And so before I start with the conclusions, I would just like to remind you that what I said in the beginning. So our conclusions are based on a simple analytical model. There are therefore limitations to those conclusions, and they should be analyzed from various point of views to derive market design solutions from such models. But the main point is that from our theoretical analysis, we do not see any such thing as a hurdle of using markets based on marginal cost pricing and capacity constraint with variable renewable energy. So there is a way to obtain an optimal generation capacity for all generators, including VRE, in markets based on marginal cost pricing and capacity constraint. So an optimal capacity of VRE can be computed as long as the renewables can be curtailed, that part of the cost of renewables has to be recovered through the markets. So the variable generators is exposed to spot prices in the same way as all other generators and load. And last thing, of course, proper capacity payments have to be made to each generator based on their on-peak contributions. And the last thing is that an interesting thing is that moving on to cheaper viable renewable generators, we can think that less expensive solar or less expensive wind could in principle get a larger share of their revenues from the markets, need less subsidies, and in the same time be competitive in the market. So with this, I thank you a lot. I guess any questions will be really welcome. I will be happy to reply to any question. I thank you a lot. Have a good day.